Hello, everybody, and welcome to a new event organized by GoLab. We are very happy you could join us. GoLab is a series of events dedicated to Go, the open source programming language developed by Google. It is a simple, fast, and efficient programming language. This is the last event before GoLab goes on a summer break. Our next event will be held in September, and we will talk about building a modular pipeline in Go for big data processing. We are also organizing a Go Advanced course in October, so we hope to see you all at our events in the fall. GoLab is organized by Develer, a company that develops hardware and software with industrial applications, with a great focus on emerging and open source technologies. At Develer, we strongly believe in supporting training and collaboration, and because of this, we regularly organize technology events like conferences, workshops, and courses dedicated to state-of-the-art technologies such as Go. Before the beginning of today's talk, I just have a few announcements. If you experience problems with the connection, if the streaming stops for any reason, remember that you can go to the email that you received confirming the event and click on the link that you find in that email. That will bring you back in the live room immediately, and you will be able to enjoy the rest of the talk. At the end of the talk, we will have a Q&A session with a dedicated Q&A chat, different from the regular chat that you can use during the talk. So we would like to kindly ask you to wait and write your questions in that dedicated Q&A chat so that we will be able to answer them live with the speaker. Finally, we would like you to join us on our Discord channel to network and share ideas. You can click on the link above us to join us there. Today's talk is about Go's profiling tool, and the speaker is Felix Geisendörfer. Felix is a staff engineer at Datadog, where he works on continuous profiling for Go. Before that, he was working on manufacturing systems for Apple, herding big PostgreSQL clusters. So we want to welcome Felix with us. Hello and welcome. We're very happy that you could be with us today.
Hello, thank you.
So we can start the talk, and we hope that you guys will all enjoy it. And please stay for the Q&A session at the end. Enjoy the talk.
That's good. Hey everybody, and welcome to my presentation, Go Profiling from Bottom Up. My name is Felix Geisendörfer, and I'm a staff engineer at Datadog since January 2021. Before that, I spent quite some time at Apple working on factory observability systems using Postgres and Go. My hobbies include open source. My GitHub README has quite a lot of information on that. I recently started a YouTube channel also about Go and open source topics, and I like playing beach volleyball in my spare time. This presentation is essentially how the profiling sausage is made. Unfortunately, this picture does not contain profiling or sausage, but we'll try to talk at least about one of those two things today. The target audience for this presentation is ideally experienced Go developers who tried to use profiling before, especially if the profiling experience includes a lot of, this is weird, how does this actually work moments, then this presentation should be very interesting for you. Beginners might still benefit from this presentation because a lot of fundamental ideas get covered and introduced. However, if you're looking for an introduction to profiling, there's probably much better presentations than this one. A lot of this presentation is based on my research that is available on github.com/data.go-profiler notes. And you can check this out if you want more information after this talk. So this presentation is called Go Profiling from Bottom Up. And the reason for that is instead of going top down like most presentations, starting with high level topics and then working our way down, we're going to do the opposite and work our way from the bottom of the stack all the way up. And this has one advantage, which is we can talk more about low level stuff, but the disadvantage is we'll talk less about high level stuff. But hopefully this is going to be interesting. So low level stuff. Assembly is pretty low level, and here we have an example program in assembly, and we just need to introduce two concepts here. In assembly, you've got these things called instructions, which is actually the stuff that's doing things, and then you've got program counters, and that's basically just like line numbers for each instruction. And very simplified speaking, CPU will execute assembly by going from line to line and executing each of the instructions. In reality, it's much more complicated than that, but for this presentation, this is a fine enough simplified model. The problem with assembly is that for computers, it's great. They know how to do stuff with assembly. Humans, we don't like assembly too much. It's difficult to read and write for us. So we invented source code. Source code is great. We like writing this much more than assembly, but computers really have no idea what source code is. They think that humans are kind of weird. So we need some help to translate between the two. And that's why we need Go or similar programming languages so we can translate. And this is in fact one of the main things that Go does is if you invoke Go build on the source code on the left, it will translate from source code to the assembly on the right. And that's great. But there's a problem. Humans are actually not very good at writing source code, despite pretending that we like this stuff a lot. And so the Go runtime needs to have a way to tell us when we're screwing up what's going on. It needs to have a way to point back into our source code where we made some mistakes. And the way that Go does this and most programming languages is through stack traces. So if you have a panic in Go, you will usually see a stack trace like this, which points into your source code, which hopefully will give you a clue on what went wrong and how to fix it. But this presents a new problem, because after Go build is done, the only thing that's left is sort of the assembly that you can see on the right. And Go doesn't really have a way to immediately, like when there's a panic, to go back to the source code and give you a stack trace. So Go needs to do some clever stuff to make this happening. And so what actually happens when you run Go build is you don't just generate the assembly. What really happens is Go generates an executable Go binary, which is a container format that depends on the platform. It can be ELF, Mako, or PE. And then inside of this container format, there's different sections in the binary. The main section is the assembly. That's essentially the code you wrote converted to assembly. But then there's also two additional sections that we're going to talk about today. One is called Go PC line tab, and the other one is called dwarf. And these sections are really helpful for making the translation between assembly back to source code happening. So what happens when we run a Go binary? When we run a Go binary, basically the assembly starts executing. The Go PC line tab and dwarf are doing nothing right now, and our Go program starts its first Go routine. The first Go routine is running the main function, and this function is getting a stack, which is a region of memory where the Go routine can put some stuff, like local variables. But also, if we want to call another function, the arguments to that function get put on the stack in Go, and lots of other things. Then what Go routines often do is they start other Go routines. So if you use the Go statement, you can start another Go routine, and that gets its own stack. And in fact, Go programs usually have many Go routines where each Go routine has its own stack. That's all great if the Go routines don't want to talk to each other, but as soon as they want to share some memory with each other, you need to put this memory somewhere other than the stack, because the Go routine lifetimes could be different. This Go routine could be sharing something with this one and then dying, but this one still wants to have a reference. And so this data then usually gets put on the heap. We're not going to talk much about heap today, but we're going to talk a lot about the stack. So one of the things that we can do with the stack is to actually get stack traces, which is where the name stack traces comes from. To do that, we take the stack, which is just a little bit of memory, and we unwind it. We're going to talk about what that means, but the end result is basically from unwinding is we get some program counters, which are these line numbers in the assembly that we talked about before. And these, of course, mean nothing to us, so we need another step called symbolization to actually get human-readable symbols like function names, file names, and line numbers that we can then identify as a stack trace. So let's talk about unwinding first. For unwinding, there's two major techniques that are used in the industry for native programs like Go. There is frame pointer unwinding, and then there's unwind tables. And we're first going to talk about frame pointers and then about unwind tables. To explain frame pointers, the best thing to do is to draw a picture. This picture right here, there's a lot of stuff going on, but it's essentially just one Go routine and its stack. And this Go routine is running 4 functions. It's running this function, calling this one, calling this one, calling that one. And each function basically puts some stuff on the stack. And in fact, if we were to call another function right now, the data for that would go at the low address area of the stack where there's some free space down here. A stack has a lot of stuff like local variables and return values and arguments that we're not interested in right now. But what we are interested in is all these red things. The first one is this one. This is a pointer into the assembly for the current function we're running, the current program counter. And then we want these other ones, which are basically the callers that are leading up to that function call. And one of the ways to get this data is through unwinding is a technique called frame pointer unwinding. And the way it works is you start at the instruction pointer register here, and that gives you the first program counter for the currently running function. Then you follow these base pointer register over here to find the first frame pointer on the stack. The return address of our caller is sitting right above that, so we just found our second program counter. And then we can follow the frame pointer, which points to the next frame pointer. And that gets us to the next return address that we can add to our list. And we can follow this frame pointer again, get another return address. And this time we notice this frame pointer has a value of 0. So it's not pointing anywhere. So we know we've now completely unwound our stack, and we've got all the program counters that are on the stack. Here is a summary of this again. We're not going to go over it again, but if you want to come back to it later. Frame pointer unwinding is actually really, really simple. I mean, this code might not look simple to you, but it's very, very little code. And this is actually a working implementation of frame pointer unwinding that in fact acts like a replacement for runtime.callers, which is a Go API for doing stack unwinding. Do not use this in production. This is just for educational purposes, but it should show you how simple, in theory, the frame pointer unwinding stuff is. So frame pointers. When you run Go build, on 64-bit platforms, frame pointers get added by default. Other platforms usually do not have frame pointers in their Go binaries. Putting frame pointers in the generated assembly means you're paying a few additional instructions for every function call to push the frame pointer onto the stack and to update the base pointer register. Doing that has some overhead at runtime. So in the Go 1.7 release notes, when this was enabled by default, the Go authors said this adds about 2% overhead for the average Go program. Now, the Linux people think the overhead can be much higher. They've published numbers up to 10%. So it might be worth measuring at some point. But if you find out that frame pointer overhead is bad for you, I've got some more bad news. Go doesn't have an option called fomit frame pointer that is commonly found in other compilers like GCC to disable frame pointers. And this means you don't get a choice. Frame pointers will always be enabled whether you like them or not. I think that's a good thing because frame pointers offer a really good way to debug program, especially if you need to debug a running program from the outside in. And taking them away just is asking for more pain when you run into really difficult production problems. Last but not least, little inside baseball. The way that these instructions are executed in the called function leads to a little race condition if you do interrupt profiling. So you can essentially miss the caller frame. So if you ever use Linux perf and you look at a flame graph or something and you see a missing stack frame, so you've got your current function being called and then there's a missing frame and then the parent caller above that could be that race condition you're hitting. You will not see that with Go's built-in profilers because they actually work differently. We'll talk about that. So despite Go build supporting frame pointers and putting them in your binaries, the Go runtime does not actually have an unwinding implementation yet. This is sad because frame pointer unwinding is really, really fast. In fact, the code I've shown you on the previous slide is about 50 times faster than runtime.callers. It doesn't handle all the special cases. For example, if you want to handle inline functions, you need extra lookup tables and you need to implement code for them, which I didn't do. But still, you would get much faster unwinding. In fact, there has been some work to look at GoToolTrace, which is Go's built-in execution tracer. And the people working on this have found that if Go runtime supported frame pointer unwinding, the overhead of GoToolTrace could go from perhaps 40%, which is really prohibitive for production programs, to something as low as 6%, which might make it feasible to run GoToolTrace against production programs. The work in progress code and discussion can be found here if you're interested. Now let's talk about unwind tables. Unwind tables are another way to unwind the stack if you don't have frame pointers. So basically an unwind table looks like this. You've got On this column, you've got program counters for pretty much every program counter in your program. And then this is mapping each program counter to the return address offset from the current stack pointer. You don't need to completely understand this right now. I'll just say that the algorithm is not actually that much more complicated. You take the current instruction pointer register program counter, look it up in this table, and then you apply this offset to the current stack pointer, which leads you to the next program counter, which you can look up again, and you keep doing this until you don't find anything in the table anymore. So in theory, it's not that much more complicated, but in practice, the table lookup code tends to be actually pretty complex. And not only complex, but also slow, because a lot of instructions have to run for executing this code. And additionally, it also causes cache thrashing during unwinding, because you have to load all this data from the unwind tables into memory. Now, this is really optimized in Go, and the very small data structures are used, but still, frame pointer unwinding is much, much faster than unwind tables. Go build adds 2 unwind tables to your binaries, not just one. One is called Go PC line tab, and one is called pprof. There's a good reason for that. The Go runtime only uses Go PC line tab for unwinding, and the main reason for that, why it's not just using the pprof one, is A, on 32-bit binaries, the Go build does not add frame pointers right now, which could be changed, but this prevents unwind tables from being used in general. But also pprof cannot be used because pprof sections of binaries can be stripped. So Go wants to make sure that your unwind tables cannot be stripped, because Go panic has to work in other things. And so Go PC line tab is used by the Go runtime always. Pprof, on the other hand, the unwind tables are used for external tools. So if you ever use a debugger or something like Linux perf with the --call graph pprof option, then you're going to use pprof unwinding tables to unwind the stack. So, quick recap on unwinding. Frame pointers are fast and simple unwinding. They have a small runtime overhead for pushing the frame pointers. There are some small accuracy issues. You have to deal with inline functions in some extra way or ignore them. And there's a little race condition for interrupt profiling. They are supported by Go build, but not the Go runtime. Linux perf, however, can use them. And that was one of the main reasons why frame pointers are enabled by default in Go binaries. Unwind tables like Go PC line tab and pprof, they are complex and slow at unwinding. Go build adds both of these unwind tables to your binaries always. The Go runtime, however, only uses Go PC line tab, and Linux perf can use pprof instead of frame pointers if you wanted to. So now quickly, symbolization. That's much simpler. We basically just take program counters and convert them into human readable symbols. So if you have the assembly on the right side here, you take each of these program counters and you essentially have a table mapping them to human readable names like function names, file names, line numbers, etc. And that's symbolization. Go build adds 2 symbol tables, Go PC line tab and pprof again. The Go runtime uses only the data from Go PC line tab because again, pprof can be stripped. But third-party tools like Linux perf use pprof for unwinding. And the final picture again is you have your stack, you unwind it, get program counters, you symbolize, you get stack traces. And the matrix of support looks like this. Unwinding and symbolization in the runtime always uses Go PC line tab. Third-party tools can choose between frame pointers or pprof for unwinding, and for symbolizations they have to use pprof. All right, there's a lot of stuff that could be improved with stack traces in the future in Go. It's kind of unfortunate to maintain 2 unwind and symbol tables in every Go binary because it increases binary size and it slows down compile times. It also slows down the runtime because you're paying for the frame pointer overhead. However, you don't even get the fast unwinding, so that's unfortunate. And so there's various proposals for improving the stack trace infrastructure on Go. One proposal is to support frame pointer unwinding in the runtime, and the other one by Rob Pike is to actually disable pprof by default. I'd say this is pretty controversial because even though some people kind of hate pprof because it's a very complex, messy format, if you have a misbehaving Go program and you don't have pprof information, it can be painful to debug it if you weren't preparing for it beforehand. All right, this is probably more than you've ever wanted to know about stack traces, but if not, there's even more information here. I also want to thank Michael Pratt from the Go team for helping me with stupid Go PC line tab related questions and reviewing some of this information. And last but not least, I want to make it worth your while that you've endured so much talk about stack traces. And so therefore, I want to hereby certify you as a full stack developer. You can now take this, get a promotion, or ask me to endorse you for it on LinkedIn. I think you now fully qualify as a full stack developer. Congrats. So let's get closer to profiling. We have stack traces now, and we need a way to store them in a file so we can look at stack traces to get like profiling visualizations and stuff. So how do we do that? In Go, there's a pprof format, and that's basically a protocol buffer format for storing stack traces. And this format contains program counters that we've already talked about and symbol information like function, file names, etc. The Go profilers always use this data format for outputting their data. And the format is actually pretty complicated. Over here, you've got a little visualization of how the pprof format looks like, but that's too complicated. Really, it's just a fancy way of encoding a frequency table of stack traces. So the data in these files are basically, it's just a table where you've got a stack trace, like this one, and then you have the number of times this particular stack trace has been seen. And that's essentially what's in the pprof file. At this point, shout out to Brendan Gregg for having a much simpler format called the folded text format that basically just looks like this frequency table above here. It doesn't support file names and line numbers and stuff, but I really admire simplicity like this in our industry where everything else is just getting more and more complicated by the day. In fact, I like Brendan Gregg's format so much that I wrote a little program called pprof to text. So you can take a pprof file from Go and get this little text output shown below, which might be useful in some cases. If you want even more details, you can use Go tool pprof with the -raw flag, and that will give you another way to look at the pprof data. This perhaps is even more useful to understand what's going on there. And finally, you can use the proto-C compiler to get a really, really raw, low-level view of what's going on in pprof files. However, yeah, you will rarely need this, but it's still interesting. Yeah, more information is available. So finally, let's talk about the Go problem here. Humans write slow code, and we need to somehow deal with it. And the way that the industry is dealing with humans writing slow code is through two techniques called tracing and profiling. The ideas are simple. Tracing, the idea is that the output is basically a stream of events, and what's included in this event data will vary depending on what kind of tracing we're talking about. In the case of profiling here, it will often be timestamps, stack traces, maybe some profiler labels, etc. That kind of stuff. But it will really depend on what you're doing. You can do tracing locally, like Go tool trace is a Go execution tracer that works for a single Go program. Or you can do system-wide tracing using distributed tracing tools and libraries and services. Tracing data can generally be turned into profiles, but not vice versa. So you can take some events and flatten them, summarize them into profiles. Tracing will often have high overhead because you have to capture every event, especially if you want to do it for runtime events, it can have high overhead. Profiling is a little different. The main difference is that the output is just a statistical summary of what happened, like a frequency table of stack traces, which often makes profiling much less overhead. And the data for profiling either comes typically from timer-based sampling or from pre-aggregated tracing data. And yeah, these are the main ideas of tracing and profiling. And they can actually be combined, as we'll see. Let's talk about tracing first in the context of Go. Let's say the blue gopher wants to know what the pink gopher is doing, and it wants to use tracing. The way it would do that is to say, hey, can you write down everything you're doing? And the pink gopher complains that this will slow the pink gopher a little bit, but oh well. The end result of tracing, as we discussed, is an event log, where here you've got timestamps and events that are happening. And an example in the Go runtime of a tool that works like this is a Go tool tracer. You can enable it, for example, in Go test via the -trace flag. But please be warned about enabling it in production. It's a fire hose that basically enables all kinds of low-level events like Goroutine context switches, and it has high overhead, 40 to 50%. As we've discussed, a significant amount of this is due to capturing stack traces, so maybe there's hope of making this fast in the future. And then last but not least, Go tool trace can be used to analyze this data including turning the data into profiles in the pprof format. Now let's talk about profiling. The main idea when people talk about profiling is timer-based sampling. And the way that this typically works is that the pink gopher is now interested in what the blue gopher is doing, and it's basically just interrupting the blue gopher all the time. It's like, hey, what you doing? Hey, what you doing? Hey, what you doing? And instead of recording every event, which would sort of be more like tracing, the pink gopher is just creating a frequency table of events. So depending on what the blue gopher is answering, it will capture the event and then just keep a counter for how many times that event has occurred. The blue gopher is complaining that it's slowing down a little bit, but low frequency makes it okay. Examples of profilers in Go that work like this are the CPU profiler that definitely works like this, and the Goroutine Profiler that you can use like that if you call it on a timed interval. The CPU profiler in Go uses the setItimer system call to interrupt and stop Go programs 100 times per second. These interrupts happen via pprof signals that are delivered to random threads, and then the interrupted thread basically takes a stack trace. The pprof profile generated by the CPU profiler looks like what you can see below. You've got stack traces, and then you've got sample counts, like how many times that stack trace has been seen. For convenience, you've also got CPU nanoseconds, but that is basically just multiplying the sample count by the fixed factor that is derived from the profiling rate, which is 100 times per second. So this is essentially redundant information. A CPU profiler has some issues on Linux, unfortunately. It works still pretty well in practice, but you should know that in some cases, the pprof signals can have some bias towards which threads they are delivered to, which can cause some skew in the profiles. And also, the profiles can become a little bit inaccurate beyond 250% CPU usage if you have very bursty kind of workloads. Various people have gotten a little frustrated with this over time. People at Uber have tried to solve this by coming up with their own way to do CPU profiling in Go. They've released most recently pprof++, which is actually a fork of Go, and it uses Linux perf events instead of setItimer. I think it's really great work, but it has a small chance of landing upstream because it adds a lot of Linux-specific code into Go, whereas the Go authors would prefer to not overfit on the Linux operating system for various reasons. Another effort that's in progress is Reese Hiltner from Twitch, who's working on a really nice patch to use timer create to fix some of these same issues. And I'm actually involved in trying to help a little bit with reviewing and testing this patch. So hopefully this one has a better chance of landing, but it's still early days as well. I will also publish more research, but I haven't gotten around to it yet. The Goroutine Profiler in Go returns a list of all the Go routines and their current stack trace. This is what it does. The main thing to know about the Goroutine Profiler is that it stops the world. So when you say, give me a Goroutine profile, the Go runtime will stop all the Go routines, and then there will be a 2 to perhaps 10 microsecond pause for every Go routine while it's going over all of them and does the stack unwinding. And this could potentially be problematic if you have 10 to 100,000 of Go routines, because then your program might be stopped for hundreds of milliseconds, maybe even up to a second, which could be a problem depending on what you're trying to do. I've developed a little profiler called pprof that is using the Goroutine Profiler for wall clock profiling, but again, it has these scalability issues, so maybe don't use it in production. pprof profiles for the Goroutine Profiler look like this. You've got stack traces, and then you've got the number of Go routines that are currently in the stack trace. It's pretty simple. What's a little bit more complicated is that there's actually various flavors of the Goroutine Profiler and APIs to use it. Here's a little summary table of the situation. And each of these ways to access Goroutine profiles will output the data in a different format and will include different information. And that's more or less a little bit annoying and something that I maybe want to send patches for in the future. But it's going to be difficult to find a better API. I have written a lot more information about this, which you can find online here. Now let's talk about combining the ideas from tracing and profiling. So you capture data via tracing, but then you turn it into profiling data right away. You could also say you're summarizing a subset of events. which is actually what the Go profilers do quite a lot. So here's an example. The blue gopher wants to know what the pink gopher is doing, but this time it's suggesting, hey, can you capture every 10th thing you're doing and summarize it? And the pink gopher is like, sure, I can do that pretty fast. So you've got two optimizations here. First of all, only every 10th event is ending up in this frequency table. And then you're not recording every event. You're just incrementing the numbers in the frequency table. And so this drastically lowers the overhead, even though you're starting with what's essentially a tracing technique to create profiles. Examples of such profilers in Go are the Heap, Mutex, Block, and Thread Create Profiler. And we'll try to talk about them real quick. The Heap Profiler essentially works like this. It's instrumenting two code paths in the Go runtime. One is malloc for allocating memory of a certain size, and the other one is sweep to free some data during garbage collection. This is highly simplified pseudocode, just meant for educational purposes. It actually is a little bit more complicated in reality. Anyway, the way that the Heap Profiler works is during malloc, there's a function that decides if the given allocation based on its size should be randomly sampled. Not all of the allocations are sampled. If yes, a stack trace is taken. And then the stack trace is looked up in the frequency table of stack traces. And we are incrementing the number of allocations for that stack trace. And we are incrementing the number of allocated bytes based on the size of the allocation. And then we are also tracking the profiled object. So the object essentially gets registered in the runtime. So when we free it, we have this additional information about the stack trace that created that object. And yeah, then this information is used again during garbage collection. The garbage collector checks if a collected object, a sweeped object, is profiled. And if yes, it finds the stack trace that created this object. And then it increments in the profile the number of frees, like how many times a object allocated at this location has been freed. And then it also keeps track of the freed number of bytes. And that is essentially how the Heap Profiler works. You can use the memprofile rate to control the sampling. By default, it aims to sample one allocation for every 512 kilobyte of allocations. And it's using a fancy Poisson sampling algorithm for that. When you look at heap profiles, they look like this. And you won't find the freeze in the profile, even though that's what's actually being tracked. In the profile, you get in use, which is basically the amount of memory that's still suspected to be in use. And that is calculated by subtracting or taking the number of allocations and subtracting the number of frees that have been tracked. And what's left is basically the amount of memory that's still in use allocated at a certain call site. Yeah, the table looks like this: stack trace, allocation object counts, allocation space, size, and then you've got the in-use objects and the in-use space. And that's pretty much it. More research on that I will do and publish. The Block Profiler is another great profiler in Go that is also instrumenting things in the runtime. Here we're looking at pseudocode for a channel send operation. So you're sending to a channel, you want to send a certain message. The first check is if the channel is ready, then the send can proceed right away. There is no block profiling. However, if the channel is not ready because it's full or for some other reason, like nobody's reading on it, then the block profiler kicks in and it takes the current timestamp. Then it waits for the channel to be ready. Then it calculates the amount of time it took for the channel to become ready, or in other words, the amount of time that the Go routine was blocked trying to send to the channel. Then it's performing the actual send. And then it's making a decision based on the duration if this blocking event should be sampled. And if yes, it takes a stack trace. And in the block profile, it increments the number of blocks that happened at this stack trace and the duration of blocking at that stack trace. The block profiler is integrated into the channel and mutex code paths, that might park a Go routine that has to wait for something. So for example, channel send while nobody's reading was one of the examples. The sampling and the recording happens after the blocking event is over and the Go routine is scheduled again. What this implies is if you have a Go program that appears to be stuck and you want to figure out why is this program stuck, you cannot actually use a block profiler until the program becomes unstuck again, because the event is only recorded after the contention is over. You can, however, use the Goroutine Profiler to some degree to help with these issues. One thing that's important, the block profiler does not track everything blocking that might be interesting. And particularly, it doesn't track blocked system calls, time.sleep, cgo, spin logs, and some other stuff. Spin logs make sense if you understand what they are, but be aware that there are some caveats to what is actually considered a blocking event and what isn't. The profile produced by the block profiler looks like this. You've got stack traces, and then you've got the number of contention events and the delay occurred at that stack trace for that contention. Yeah, there's also some control. You can use set block profile rate to control the sampling rate. And my research indicates that 10,000 is a pretty safe value for production. If you're not sure what to configure, configure 10,000. If you configure something less than 10,000, there's a chance if you have a very heavy blocking workload that you might see some high overhead. So 10,000 is a good starting point. While I was researching this profiler, I discovered something, namely that the block profiler had a sampling bias that was favoring infrequent long events over frequent short events. And so I created and submitted a patch for upstream, and it's been accepted. It's going to be released in Go 1.17. That's going to fix a bias in the block profiler, which will hopefully make it more useful in the future. This will probably not affect you if you've had configured a very low sampling rate, but for high sampling rates, this patch should make a difference. Much more information on the block profiler can be found online. The Mutex profiler is very similar to the block profiler, but it's focused on mutexes exclusively. There is some overlap. Both profilers, block and mutex, can profile mutexes, but the difference is the mutex profiler is instrumenting the unlock code paths, unlike the block profile, which is instrumenting the lock code paths. And what that means is that the sampling and recording for the mutex profiler happens when unlock unblocks another Goroutine that was blocked. In other words, if you see stack traces in a mutex profile, that will tell you which locations in your code were blocking other Goroutines from proceeding. So you find the source of the contention, so to speak. And the block profile, on the other hand, will tell you the opposite. It will not tell you the source of the contention, but it will tell you the victim. It will show you which code was waiting and couldn't proceed because somebody else was blocking. So there's good reason to enable potentially both profiles if you want to debug lock contention in Go. You can use the runtime set mutex profile fraction to tune the sampling rate. And the profile actually looks exactly the same in terms of the columns here as the block profile, and semantically means the same as well. Yep, more research coming. And last but not least, actually it is least, the thread create profiler. As far as I can tell, this is not working. I found an 8-year-old issue or something that says that this profiler is broken. In theory, it should capture stack traces that cause new operating system threads to be created. And the profile should look like this. Just a stack trace and how many threads, operating system threads were created at that stack trace. But as far as I can tell, it's not working. So you might not want to enable it because it's broken. So that concludes this presentation, but we've got time for a final small recap. The fourth small recap is that stack traces are a load-bearing component for profiling and tracing, and understanding how they are created can help you use tools better, choose which tools to use, etc. Go profilers, different Go profilers work quite differently using tracing techniques, profiling techniques, and kind of hybrids between the two of them. And yeah, my hope is that understanding these implementations will make it easier for you to use Go profiling correctly and safely in the future. Yeah, thank you so much and for listening. And if you have any questions, please find me on Twitter. I'm happy to help you with anything. Thank you.
Hello again. And of course, if you have questions, you do not have to wait until you get to Twitter. You can ask them right here in our Q&A chat that will be enabled very, very soon. So we can welcome back Felix, and will be waiting for your questions. Thank you, Felix, for a very interesting talk. And let's see if our users want to ask something. You got some compliments for your T-shirt. I saw.
Thank you.
That's really cool T-shirt.
Yeah, I miss that computer. The Commodore 64 was a right? great machine. When you were kind of forced to learn programming, all I wanted to do was like load a game, and you had to like load the disk, list the programs, and then run them. Really but that kind of hooked you already.
Okay, so first question is coming. You mentioned that some people consider dwarf to be kind of evil, but what exactly do you mean?
So what I mean by that is that when I say dwarf is a complex format, that is probably a very kind understatement. Dwarf is a really, really complex format. In fact, dwarf supports expressions inside of the dwarf section that are executed when, for example, stack unwinding is happening. And the language for these expressions is actually Turing complete. It's a Turing complete VM that is executing dwarf expressions. And there was a recent paper called Exploiting the Hardworking Dwarf, Trojan and Exploit Techniques with No Native Executable Code, where some security researchers actually took advantage of this design choice in Dwarf to exploit applications through Dwarf as an attack channel, which may not be very relevant in practice, but it's certainly very interesting and shows how complex of a beast it is.
Okay, thank you. Okay, this is okay. I was wondering about heap profiling. I understand that it's based on sampling with Poisson distribution, and it targets one sample per 512 kilobyte of allocated memory. Is it possible to confuse the sampling such that profile will be very inaccurate? In other words, how precise is the heap profile? One sample of 512 kilobytes sounds small to me, but I couldn't confuse the sampling to give me wrong results.
That's a very good question. The answer is I don't know for sure. So far, I've mostly looked at the Goroutine Profiler and the block profiler. With the block profiler, I found such a way of confusing the profiler into giving wrong information. With the Heap Profiler, I haven't found it yet, but I haven't also looked as hard as I'm hoping to in the future. But I would say that even so one sample out of 512 kilobytes sounds very little, in practice, when a Go application runs for a while, you will often see it allocating gigabytes and terabytes even of memory over its lifetime. And I would assume that given enough samples, the statistics work out that it's relatively accurate. But I could imagine for very small, short-running programs that you get very wrong profiles. But I don't think it's a problem in practice for continuous profiling. I will do more research on that, and try to get better answers.
Thank you. So, is anyone working on enhancing performance support for Go?
So the question is enhancing perf support, which could mean Linux perf or profiling performance. I don't know anybody working on Linux perf, if that was the question. I also don't know if there's any significant problems with it right now. As far as profiling in Go itself, that is at the very least being worked on by a few people. I mentioned that Reese Hiltner from Twitch is trying to improve the CPU profiler bias issues, and I'm trying to help review him. But I also see a few other ongoing issues that are being worked on, such as frame pointer unwinding support for the runtime. I'm certainly hoping to make more contributions going forward.
and we're all looking forward to seeing them. Which is the most common hidden issue that a profiler helps discover?
That's a good question. I don't know if the profiler helps discover it, but I think what a lot of people are surprised by, maybe not, is that a lot of CPU time is actually being spent by Go programs is going into garbage collection, both on the allocation code pass as well as the deallocation code pass. And so people often manage to get 20 to 30% CPU time improvements on their Go programs by looking at the heap profile and optimizing the allocations and reducing them. And that might be, a good hidden thing to be aware of.
All right. Is it profiling possible when building with TinyGo?
I do not know. I think TinyGo is for embedded, but I've not looked into it to answer that question.
Fair enough. Do you plan to, or do you know anybody who plans to consider using eBPF probes to collect Go profiles instead of asking the Go runtime to do it?
I think that there is various efforts in the industry and perhaps even open source space to do that. I don't know if anything that I could link to right now is out there that would be widely available. My understanding is with eBPF, it doesn't really change the story much on how to unwind the stack and sort of interrupt. I think you could do that with perf for a very long time on Linux perf. The only improvement I would imagine eBPF to provide is that the aggregation of stack traces could be done without context switches to the kernel. So it might reduce the overhead a little bit. And as mentioned, you might actually get better accuracy as well because the built-in profiler has bias issues, but those are not due to eBPF versus just using raw perf events. That's due to the signals that are being used. So it's a good question, and I think there's a lot of interesting stuff going on with eBPFs that will probably lead to new products and profiling methods going forward.
Very good. See if we have some other questions. Okay, CPU profile using SIGPROF interrupts random threads, which then takes a stack trace. Is this stack trace of every running Go routine on some thread, or just Go routine on the interrupted thread?
That's a good question. It is the stack trace from the Go routine currently running on the interrupted thread. The hope is that the set iTimer will fire in response to a thread that is currently running on the CPU, using up or pushing the CPU time of the process another 10 milliseconds forward, and that triggers it. So the thread that's getting the profile should be the one that was lost doing CPU work. But yeah, it's definitely not all of the Go routines that get profiled at that time, as that wouldn't scale and wouldn't also wouldn't make sense for CPU profiling, because you're trying to identify the code that's actually spending CPU time rather than wall clock time. Wall clock profiling is a separate thing that Go would benefit from. I've got this FGProf project that I mentioned before, but there's more work to be done to make something like that scalable.
How does the profiling overhead increase as a function of the number of cores or configured? I'm not going to read that.
Okay. Go max prox.
Go max prox.
Yes. The honest answer is that I want to do more studying of that, and I actually got a project in the pipeline to get more data on this to answer this with more confidence. Because of the one issue that I mentioned in, I think I mentioned about the CPU profiler that's currently limited to a max sampling rate of 250 Hertz, there's sort of an upper bound on how much overhead the CPU profiler can introduce. And so I would think that flattens out and stays within a few percent, but Yeah, it really depends on whether that gets fixed. If that gets fixed, I would imagine it to actually go up probably linear with the number of CPU cores that are being utilized. But again, I hope to do more rigorous analysis and publish data on this going forward.
Thank you.
These are very good questions, by the way, and difficult questions as well.
Yes, like they are all very precise and very detailed. And okay, so, I was wondering how your company benefits from your work on Go profiling. I don't know if you want to answer this. I mean, if you don't want to answer, that's fair.
I mean, first of all, I hope they benefit, because otherwise I might need another company that would want me to work for them. But so far they seem happy and I'm happy. I would say the answer is, well, I'm not just working on open source Go profiling, I'm also working on the product and push that forward, make that better, enhance the experience of people. But also the hope of like doing open source work, presentations like this, and contributing back to the community is that my company Datadog will be seen as a friendly player in the profiling community, and that somebody who can be trusted with your data and give you good answers on where your programs spend time. Hopefully that makes sense and will work out.
Yeah. All right. Any opinions on continuous profiling tools?
Yeah, I don't need to re-mention that my company offers one. There's a bunch of open source ones out there. I would say that they generally fall into two categories. They're either going to be built based on Go's built-in tools, which is largely what this presentation was about, or they're going to be based on Linux pprof, which is another way, or maybe eBPF, even some more modern ones. The major difference there is with the Go built-in stuff, you kind of have to enable profiling in your program through some library or something, whereas with Linux pprof and eBPF, you can potentially profile a program without changing it, without recompiling it. And the other thing is that Linux pprof and eBPF might be a little bit more accurate, but you're not getting as deep insights into the runtime. So you will only get, for example, a CPU profile. You will not get an allocation profile or a clock profile or mutex profile, generally speaking. With eBPF and uprobes, a lot of things are possible, but from what I've seen, what I just said are probably the major trade-offs, and you can kind of compare products by thinking about them like that.
Okay, so is there a way to profile and recognize the connection pool over DB connection?
I would say for something like that, you'd probably have better luck instrumenting a connection pool with traditional metrics, time series data, where you just count potentially how many connections the pool has maximum, how many connections are in use, how many are idle, and from that you can derive important things like the utilization of your connection pool. I'm assuming this is the connection pool inside database SQL in process in memory. So that would be one way to instrument that. The other way would be distributed tracing. For profiling, I would have to think a little bit on how profiling would help there in particular. I think the other techniques will be more likely to produce good insights to that.
Right. Are there other tools that can be used to visualize instead of flame graph?
There are, in fact, a few other tools. I wish I had the list right now. There is, let me see if I have it in my notes. Flame scope. I will have to check my notes later on. But there's at least two tools that I'm aware of that are somewhat compatible with pprof files. And so, yeah, there's a few other viewers out there. I would say that most of them, however, tend to also show flame graphs. There's a few tools that try to, like a flame graph doesn't the x-axis is not time, it's just duration, but you don't know the order in which things happened. There's a few tools that show you things in order, but unfortunately the Go CPU profiler doesn't collect the data in a way that would make it possible to display it like that. Everything gets aggregated and the timestamps get thrown away. So the tools that can do those visualizations don't work for Go profiles. But it would be really cool. Like, for example, in Chrome DevTools, you can look at JavaScript profiles as a flame chart where the x-axis is literally time. They have a higher sampling rate. They sample with 1,000 interrupts per second rather than 100 that Go uses, which I think you would also want for that to be useful. But yeah, for Go, I would say flame graphs are the dominant way to visualize, together with the graph view that pprof used to ship by default. Maybe it's still the default, actually, I think, in GoTool pprof. Yeah, then you can also show a tree map or sunburst diagram. I've seen that, but I'd say flame graph to me is the most readable out of those options. Yeah.
Okay. All right. With so many CPUs available, could it not be a good idea to just dedicate one to profiling?
I'd have to think about how that could work. Because the key idea is you want to observe what's happening on all the CPUs in your system. So even so, you might dedicate one CPU to do something like the aggregation of the information. You still need to set up at some level hardware interrupts for each of your CPUs to stop, which in the case of Go profiling is done indirectly through that iTimer, which is a software interrupt mechanism that is built up on hardware interrupts. But you, under the hood, you set up hardware interrupts for all the CPU cores. And I don't think I can think of a technique that would get around that and really centralize the profiling overhead to a single CPU core. You'll probably have to use interrupts on all the CPU cores your program is running on.
All right. All right. Now the question, is it possible and is it easy to add custom application-specific profiles? Do people do that? It sounds to me like it could be useful, but I've never tried.
That's a very good question. I tried to do this once myself when I was working on FGProf, the wall clock profiler for Go, and I found that the interface for adding your own profiling information was not suitable for what I was trying to do. I forgot what the limitation was. However, I think probably the limitation was that I couldn't provide my own stack trace. So I had already collected the stack traces myself and wanted to add them to the profile. And I think the assumption on the current API was that if you increment an event in one of your custom profiles, the stack trace is taken at that time. And so I found it limiting. The main use case I would see for adding your own custom profiles is perhaps to count some resource that you care about internally, like running database queries or open file handles or something like this. These have been the examples given by the Go authors of file handles. I haven't seen it used much like that in production. If you have examples, I'd be interested to look at them, but it's not getting much use.
Okay, so maybe we can close our Q&A session here. And if you have more questions, you can, of course, join us on Discord. And here's the link. And Felix maybe will be so kind as to answer some questions there as well.
Sure thing, I will be there.
We would like to thank everybody. Thank Felix for being with us, and thanks the whole audience for being with us and providing such a lively Q&A session. We're very glad to see so much interest. If you have other questions for us, you can always write to us on Discord or at info@golab.io, or you can follow us on social networks. So I just would like to remind you about our 2 events in the fall, one in September and one in October. Please stay tuned and join those events. All our sessions will be available on YouTube in the GoLab channel. And you can stay up to date by subscribing to our newsletter. So thanks again to Felix, thanks to the whole audience, and we hope you enjoy today's talk. Goodbye.
Yeah, thanks for having me, and I want to second that the questions were excellent. This was really, really interesting.
Thank you very much. We are very proud of our audience then.